Hi, this is our second part about polar area. Thanks for muscling through those three little videos that I called video one altogether. See, that's just cheap, right? I always wonder as a teacher why people ask me how many questions are on the test because I could say three and they could all have multiple parts. You know what I mean? So one video, three parts. I mean, really, wasn't that three videos? Anyway, so here's the last one. I think I'm going to do this all in one fell swoop, hopefully. And today we are looking at finding area between polar curves. The two keys to this are going to be remembering to figure out points of intersection. So you're going to have more than one curve. And just like in a rectangular context when you're finding area between curves, you need to figure out those points of intersection where the top and the bottom switch places or where the region begins and ends. And so that's basically what is happening here as well. And then the other key, and this cannot be emphasized enough, is to remember to draw in or at least think about the different wedges and how they come into play as you kind of sweep around the curve. And that's going to be important because you can't just be thinking top and bottom like you can in rectangular life. You have to be thinking about all of those wedges and how they interplay between the two curves. You'll see more about that as we go through. Now, if we were in class in the same room together, I would have you all do a little warm-up exercise on pages 38 and 39. So on page 38, you see free response question, polar form, polar problem. It's calculator active. And I would give you maybe 10 minutes to work on that. Maybe not enough time, but around 10 minutes. And then I would ask you to turn to the copy of the same exact question that's on page 39 and buddy up with someone and do the parts that neither of you could figure out maybe by yourself completely. So like not start from the beginning again. And if there was something you both got, not to do that over again, but just to fill in the gaps. And the point of that, in my opinion, is if you look at those two pages, then when you're studying later on, you can say, all right, 38 is the part that I got on my own, 39 is the part where I needed support. And that can help point things out to you as far as your own review when you're studying for the quiz on this. So that would be our beginning exercise. If you want to try that now, you could pause the video, do so, and I can be your partner in that I put my work up on Schoology. So you can take a look at that and, do the same sort of thing that we would do in class. If you are listening to this in class or if you want to try to do that exercise tomorrow, you could do that with a classmate. There's no urgency to when you do this, just sometime before the polar quiz I think would be in your best interest, just so you see how College Board tends to ask questions. All right, so now delving into the lesson itself, we have two example problems to do. They both are going to utilize the same picture, but the words that are with them define different regions. And we really want to take our time when we read the question to make sure we understand the region that's being asked about, being defined. So this one says find the area inside of r equals 2 cosine 2t. Notice here I used a t instead of a theta. That was purposeful because I don't want you to get married to the use of variable, right? College Board often tries to mix things up just for, being spicy, I don't know. And then the area that's outside of r equals 1, which is the red circle. So inside the purple, outside the red. Okay, so that seems reasonably straightforward in terms of the region because I think I can just go on my picture here and say, all right, well, that means this yellow region, for instance. And then similarly on each of these, right? It refers to these little outside bits of the petal. Okay, so I understand that that's what's being asked for. The thing that's going to be trickier about it is the fact that we are indeed in polar world. So we need to think about how to define the space. We are going to be using our same integration setup, like the 1/2 and the r squared d theta, like that's going to be a thing still. But if you think about just the purple part of our curve, right, there's going to be some amount of the curve, sorry, I am not very good at this. Okay, there's going to be some amount of the curve that is determined by these lines that come out. Okay, so at some point we're at the pole, and then as you sweep through, like let's say that we're about here. Okay, so going from that juncture. And as you move through, these are all the little wedges that would be defined by the purple curve. Something really interesting is about to happen right here. Okay, sorry, that was like maybe the least straight line ever. Okay, so there are all these little wedges that are coming out, right? Da, 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 da. And then you get to this point, and then at this juncture, like the wedges that would be like right here, do we want to include those or not? Think about where the yellow highlighting was. And I hope you said not. Okay, so there's this little green sliver that would happen over here. And then there's going to be a little green sliver over here that we don't want to include. But what we do want to do is start from this point that I just made blue. We want to take all of these wedges, starting from the blue point, take all of these wedges, all of these other black wedges I already drew in, and then we want to stop when we get to this second blue point so that we don't include the little green slivers. Okay, so do you see how it's really important to draw out all those wedges? I think it's really, really important to understanding the question, that you think about how the area gets swept around as the point, like as the polar graph would be created. Okay, so I erased all that now just so it would look more neat, and I can say, all right, I want to start from that point, whatever theta value gives me this location on the purple curve, and I want to go to this location on the purple curve, and I'm going to find all of the area for the between those 2 points, all of these wedges going out to the purple, and then I'm going to be subtracting all of the parts, lacking another color. I'm going to subtract all of the things between those two. Like I'm going to subtract all of this yellow line part. Okay, so we're going to have, that looks very scout-like. We're going to go all of the purple wedges from the blue dot to the blue dot from A to B, and then we're going to subtract all the yellow part. Okay, so it seems to me we need to know what the points A and B are. Do you have an idea about how to do that? It is where those curves connect, right? So we need to find a point of intersection. So it sure seems to me that I just want to set these two equal to each other and solve. And then I want to have those values determine the bounds. And then my integral is going to have some subtraction because I have all of these blue wedges that go out from the pole, right? All of these, and I want to subtract off that inner part. Probably I layer every color on here, you'll understand better, probably. Okay? I'm asking you to pause this, set up, find the points of intersection, set up the integral, and then come back, okay? Okay, so I hope you successfully found the bounds. That writing on my work is in blue, and so you can see I just set up the equation, solved it like a good old trig problem. I decided to stick with looking at this petal that is on the right side of the graph. You could pick any one of the petals, but that meant that I was looking at negative pi over 3 and pi over 3. I was thinking in particular in solving this about the unit circle. And so I know that cosine is equal to a half here and here. And so I would have this spot, which would be pi over 3. And then as I would come around again, that would be adding a multiple of 2 pi each time. And then this value on the unit circle is negative pi over 3. And then the same z's for the adding 2 pi each time around. And so my solutions were then negative pi over 6 and pi over 6, or whichever other ones if you picked a different petal. And then underneath the purple line, you see that I set up my integral. And so this integral just says, hey, we're going to take the wedges that go out to the purple curve, starting from the red dot, so starting from when theta is negative pi over 6, just past that, wow, just past that, you're going to get some wedges that are like these. Right, so I'm getting all those purple wedges from this first part of the integral, and then I want to subtract off, starting from the red dot, and then going past that, all the red wedges that I would get. And that'll leave me with the region that I talked about at the beginning that I had with the yellow highlighter, this part out here. Okay, so that's the idea. And then if you did need to do some part of that by hand or all of it by hand, this is just part of the integral. The subtraction of the sector you actually could do with geometry, to be honest. So if you needed to evaluate this integral, you would do your typical sorts of things. 2 squared is 4, and I have a half, so I took out all of my multipliers. And then I would need to use my very favorite trig identities, little u substitution, and so on if I needed to do this by hand. But honestly, use your calculator to evaluate any integrals if you're given the option, because this just takes a little while, okay? Not hard, but just a pain. All right, so for the second question, again, this is the same picture, so the same two functions, but the phrasing is a little bit different. So here we want to find the area that is inside both curves simultaneously. So let's think about what that might refer to. So area that is inside the purple curve would be like all of these, right? All of these regions. And then inside of the circle is this part. And you say, okay, well, I understand now. That's pretty straightforward to see what we're talking about. It's basically the overlap part. So if I were to highlight this like we did last time, it would be I want this region in here. Okay, and I also want this region, and I also want this region, and I also want this region. Okay, and so I could find one of those regions and multiply by 4, okay, just like we talked about with the previous question. I did say that, didn't I? The multiplying by 4 part? Oh, maybe I didn't. Okay, so in this question, this is to find one petal, and then at the end of that, right, because the question was actually for the whole shape, then you would multiply by 4. I didn't actually say that, maybe. Okay, sorry about that. Okay, so here, if we want to find this yellow region, okay, we need to think about how this is defined. Okay, so there's, again, just like since it's the same picture, part of the advantage of the same picture is we don't have to like refigure out every single thing. But we do know that there's some important points. This point here and this point here, okay? And we know that we do not want any of this region, so I'm going to write no, don't want that. Okay, but I do know that something interesting happens as we sweep through the polar curve and points are being made, points are being plotted like through here. And then we get past the blue dot and we're out here, right? Something transitions right there. So I'm going to draw in a little line. So there's a wedge that would come here, and there's a wedge that would come right here eventually, okay? So we do want to include the sector of the circle. So I'm going to use a highlighter again, I think. We do want to include the sector of the circle in here, right, this region. But we also want to include these little itty bitty guys, right? We want to include, I'm going to make these green. I think I made them green earlier, right? So this little part and that little part both need to be included as well, okay? So those are the different pieces that we have. This, the green slash highlighted blue shape all together, that's the region we're searching for. And that has some symmetry. So I'm going to make use of the symmetry and just say, all right, let's cut this in half. And then let's just work on part of it. Okay, so let's go from 0 to pi over 6. Okay, so from 0 to pi over 6, getting the blue part. Here, I'll try to color code a little. Okay, so the region that's highlighted blue on this one petal. So let's make sure we make a note that this is just for one petal. I'm going to have double because I have this part and this part. Okay, I'm going to have double what I'd get from 0 to pi over 6. And that part, I just want the circle. I want my wedges just to go out like this much. Okay, I drew those out of order in terms of the angle, but hopefully you went with me. Okay, so 1/2 r squared d theta. Okay, so that's going to be the blue part. The green part, okay, again using the symmetry, so if I use the bounds, color. So if again I use the bounds that I had above, 0 to pi over 6, I'll need to double that because the 0 to pi over 6 is just giving me this top zone, okay? And then I want to go from here to here. So the task is then to figure out what angles, well actually I have the wrong bounds. I know that's not going to be it, sorry. So I want to go, that was almost a mistake there, heek. All right, so if you kind of explode this out to be kind of large, there's this black line, and then there's this purple curve that's coming back around. So I need to know when the purple curve hits here and when the purple curve comes back to the pool, like here, right? So this little enlargement is this green zone here. So I need to figure out when the purple curve comes back to the pool. Okay, so that's a little side problem that we're going to do. Okay, so the purple curve coming back to the pool, purple curve is this equation. Coming back to the pool means that. So that would be 2t equals, let's see, that would be pi over 2 plus, like going the top and the bottom of the unit circle, so multiples of pi. And so my t would be pi over 4, and then every 90 degrees after that. Okay, so if I think back here at my picture, I know that this was at pi over 6. So this must be pi over 4 for my purple curve, right? If it just goes out here 0 and then going through the angles of the first quadrant up until 45, okay? So, so the green part is going to have double because I'm just doing the top. I also need the bottom. And then from pi over 6 to pi over 4. And then 1/2 r squared dt. I just realized I have a d theta up there, don't I? Thanks for pointing that out to me. Okay. A little bit of me wants to go back and re-record this, but that's just not going to be the case. Okay, just for that one little mistake. All right, so we have one petal. It's going to be this blue part plus this green part, okay? We would find that result and multiply that by 4, and then we would have the full answer for all of the things that were initially colored in yellow. All right, so that's as much as I think we're going to do together. There are 2 more problems, number 3 and number 4, in your packet, and I will have my answers for those up online by the time you're listening to this, hopefully. So you can check those 2 examples, and you can check the free response question against my work that's online. Priority, though, is honestly to make sure that you do the book assignments, help each other out, and let me know if you have any troubles, okay? And we will put everything together when I'm back. Thanks so much, you guys. You're awesome, and thank you for understanding. Bye.